Hey everyone, Mr. Calc here. In this video, we're going to go through the 9.8 Polar Calculus Day 3 notes. Alright, so let's go ahead and get started here. I'm going to try to see if the screen recording is going to allow me to exit GoodNotes and open up Desmos, because this is a very, very visual topic. If you don't have a good visual going, this can be a very difficult topic to understand. Hopefully you have your TI-84 next to you, ready to go. The first thing that we want to do is I want you to go ahead on your graphing calculator, select mode, and change the option from sequential to simultaneous. What this is going to do, and by the way, we should still be in polar from yesterday. If your calculator's not in polar, maybe you had to work in degrees with physics or something, go ahead and change your calculator back over to polar. But what this should do, because we're going to be graphing multiple polar curves at the same time, it should graph them simultaneous with each other, and you should be able to see them, graph in real time. Okay, I'm going to be attempting to use Desmos so that hopefully we have some kind of visual, but yeah, we'll see. We'll see if I'm even able to record it. All right, so in this set of notes, one of the main things we want to be able to accomplish is figure out how can we find the area bound between two different polar curves, okay? So what we're going to have to do, this is an example one right here where we already have a visual. So, and a lot of times, not all the time, but a lot of times, these are calculator active problems. And one of the benefits to these being calculator active problems is we can use the calculator to graph a very specific window of these polar curves to make sure that we're looking at the correct area that we want to, that we're trying to bound, okay? So this says, example 1, find the area inside of r equals 3 sine theta and outside of r equals 2 minus sine theta. Okay, so inside r equals 3 sine theta, this is the circle, this is this blue circle right here. And outside r equals 2 minus sine theta. That's this polar curve right here. It's not quite a circle. All right, so inside the circle, outside of the green polar curve. So what we're actually looking for is we want to calculate the area of this piece. Okay, that's what we're trying to calculate the area of. So let's go ahead and label these again. That circle there, let's call this R1, and this is R2. All right, so what we want to do is, first off, we need to find these points of intersection right here, where these two curves intersect each other. To find their points of intersection, we're going to set the two polar curves equal to each other, and that's how we're going to try to find the points. So for the points of intersection, let's set these two polar curves equal to each other. 3 sine theta equals 2 minus sine of theta. Let's go ahead and add sine of theta to the left side. Now we're going to have 4 sine of theta equals 2. Divide both sides by 4. Sine of theta equals 1/2. And we want to get all the different angles that sine of theta is equal to 1/2. Okay, so that'd be pi over 6, 5 pi over 6, and then you could continue going on. You could get coterminal angles to these. So coterminal to pi over 6 would be 13 pi over 6 if you added 2 pi to it. Coterminal to 5 pi over 6 would be 17 pi over 6. And we know these go on forever. Okay, so I'm going to go ahead and claim that this intersection point is the pi over 6. This intersection point is the 5 pi over 6. One of the reasons it's really, really important that we have a visual, something like Desmos or your TI-84, is because what we can actually do, and again, I'm going to attempt to show this in Desmos, we can try to graph both of these in Desmos or your TI-84 when it's set to polar mode. And if you restrict your theta minimum and theta maximum to be pi over 6 and 5 pi over 6, you're actually going to see on the graph that it's only going to graph this piece right here. Okay, so let's attempt to move to Desmos. Hopefully it doesn't shut down the recording. All right, so if you're in Desmos, you can use your TI-84 set to polar mode too, but if you're in Desmos, you would click this wrench in the top right corner, you would click that little polar icon. In R1, we would put R equals 3 sine of theta. You need to actually use R and theta, so R equals 3 sine, and then you can type theta, or theta is actually right over here, but you can also type theta. Okay, and then our second one was R equals 2 minus sine theta. Okay, notice how under each equation it says 0 to pi, 0 to 2 pi. Let's go ahead and restrict it to pi over 6 to 5 pi over 6 for each one. And you see how when we restrict each one to be from pi over 6 to 5 pi over 6, it's showing the area that we're actually trying to calculate, okay? Which is why having a visual is really, really nice. All right, so now how do we actually calculate the area? Well, to calculate the area, it's going to be similar to what we did yesterday. We're going to say the integral from pi over 6 to 5 pi over 6. Now, these are two different curves. The way that it works, when you want to calculate an area bound by two different polar curves, the curve that is the furthest away, so notice this area we're interested in. The top bounding curve is from R1. The bottom bound of the area is from the second one, R2. Okay, it's from this one. We want to go furthest curve minus closest curve to the pole. Okay, so notice that for this area here, the top curve, R1, is further from the pole than the bottom curve would be. Okay, so it's going to be 1/2 of R1 squared minus 1/2 R2 squared d theta. Okay. Go ahead and throw that into the calculator. Please double check that you get the same number that I have, 5.196. And you'll see if you look at my key to the notes, you'll see that I take these 1/2 and I factor them to the outside. And I have it look like that. You're more than welcome to do that if you want to, but I figured I'd leave it like that to kind of follow along with the area formula from yesterday. Okay. Example 2. Find the area of the common interior of r equals 3 cosine theta and r equals 1 plus cosine theta. Okay. This one I remember in years past giving students kind of a headache. So let's kind of talk our way through this. So r equals 3 cosine theta, let's go ahead and call this r1. R equals 1 plus cosine theta, let's go ahead and call this r2. Okay, just so we have some common naming here. And let's go ahead and get a visual of what this is going to look like. So I'm going to jump back over to Desmos. Hopefully the recording continues. All right, so our R1 is going to be R equals, our R1 was 3 cosine theta. And our R2 is 1 plus cosine theta. Okay, so we get this image right here. All right, so I'm going to try my best to make a picture of this based off of what we just saw in Desmos. My picture is, of course, not going to be perfect, but oh well. All right, so we had the 3 cosine theta was a circle, diameter 3, like that. Could be a little better, but we'll go with that. And then the other one was kind of this. Actually, no, I'm going to do the circle different. Didn't like how it wasn't really symmetric. Yeah. One more time. Third time's the charm. That looks better, I guess. All right. And then the other one, so this one was R1 that we just drew. This was the circle, diameter 3. And then the other curve kind of looks like this. It was like that. Okay. And we want to find the area of their common interior, their overlapping interior. So we're looking to find this area right here. Okay. Now, let's talk strategy as to how we can actually find this. If we take this whole circle and we subtract off this kind of crescent moon shape, it would give us this. Okay, that's probably what I think would be one of the easier ways to calculate just that. All right, so this is circle minus the moon. And this was R2. Forgot to label that. Okay, so the question is, we need to find these points of intersection. All right, we need to find the points of intersection. All right, let's set these two equal to each other. 3 cosine of theta equals 1 plus cosine of theta. Let's go ahead and subtract cosine of theta to the other side. 2 cosine of theta equals 1 divided by 2. Cosine of theta is 1/2. And that's going to happen. Cosine will be 1/2 when theta is pi over 3. 5 pi over 3. 7 pi over 3. That'd be the coterminal one to pi over 3. Coterminal to 5 pi over 3 would be 11 pi over 3. Just add 2 pi to it. ... All right. So this is where the visual is really, really important. Again, we want to do the full circle minus this crescent moon to get what I have here in red. Okay. My strategy is I actually want to calculate. We need to calculate the. We need to calculate this crescent moon so that we can subtract it from the circle. The circle is easy to calculate the area of, pi r squared, right? The circle is really easy to calculate the area of. So I actually want to calculate the area of this crescent moon and subtract it from the circle. So in Desmos, I want to figure out which sequential angles can I make my theta minimum and theta maximum to only give me the moon. All right. And watch what happens. If you do pi over 3 and 5 pi over 3, you're actually going to notice that it doesn't work. So let's try it. over 3. There we go. That definitely is not the crescent moon, right? So let's try the next two. The next two were 5 pi over 3 to 7 pi over 3, 5 pi over 3 to 7 pi over 3. And notice that that actually gives us the crescent moon. Okay? So we actually want to use these two for the moon, for that moon shape. Okay, so we're doing circle minus the moon. The circle's area is very simple. We know the area of a circle is pi r squared. The radius of this circle, that's a diameter of 3, so the radius is 3/2. So pi times 3/2 squared minus, and now the area of the moon is going to be the integral from 5 pi over 3 to 7 pi over 3. You can pull that 1/2 to the outside if you want. I'm going to go ahead and do that actually. And then we're going to have furthest, so remember when we're calculating the area, it's the curve furthest away from the pole, that's going to be our R1, minus the curve closest to the pole, that's going to be, this boundary is coming from R2. Right, so R1 squared minus R2 squared d theta. Okay, and remember, you can either have the 1/2 on each one of them, or you can factor the 1/2 out. Doesn't matter. This example, I factored the 1/2 out. Okay, go and throw that into the calculator. Make sure that you get 3.927. Always double check in the calculator. Make sure you're not goofing it up. All right, 3.927. All right, example 3. Find the area of the inner loop of r equals 1 plus 2 cosine of theta. All right, let's get a visual. R equals 1 plus 2 cosine of theta. Okay, notice there's an inner loop right there. Okay, there's an inner loop. So we notice that it's not two different polar curves. We can't find a point of intersection for these two different, because there's not two different polar curves intersecting. But notice that the inner loop is hitting at the pole. Okay, if you especially on your TI-84 where you can see it trace, when you watch this polar curve trace on your TI-84, you're going to notice that it hits the pole, does that little loop, the inner loop, and then it hits the pole again and exits. Okay, that exits the inner loop. So we can set this thing equal to 0 and find the angles where it hits the pole. All right, so let's go ahead and do that. Let's set this thing equal to 0. 1 plus 2 cosine of theta equals 0. 2 cosine of theta equals -1. Cosine of theta equals -1/2. And that would happen, cosine to be -1/2 at 2 pi over 3, 4 pi over 3, and then you can add 2 pi to each one of those to get some coterminal angles, 8 pi over 3 and 10 pi over 3. Okay, and if you actually try the first two, if we have our theta minimum and theta maximum be 2 pi over 3 and 4 pi over 3, you're actually going to see that we get the inner loop. So let's show it. 2 pi over 3, 4 pi over 3, and now you see that from the Desmos picture, we only get the inner loop. So that's how we're going to use those for our integral. All right. So The area of that inner loop is going to be the integral from 2 pi over 3 to 4 pi over 3. Again, you can pull the 1/2 out. Let's go. I guess I'll go ahead and do that. 1/2, that's from the area formula from yesterday, of 1 plus 2 cosine of theta squared d theta. All right, make sure that you are calculating that and that you get 0.544. Right. Example number 4. We did examples like this, I think, in the previous set of notes, in the 9.7 notes, where you have to calculate dy dx, which is then dy d theta over dx d theta. So I'm going to have y'all try example 4, A and B on your own and check with the key online instead of me going, through those examples again. Okay? So try those out. Remember, you're going to have to calculate x is r cosine theta, y is r times sine of theta. You have to take the derivatives of find dy d theta and dx d theta separately. So do all that stuff. Check the key online, but for the sake of time, try that problem, check with the key online. All right. Let's do some FRQ style problems. So the 2 examples on the back are free response style problems that you could see on the AP exam, okay? So example 5 here, calculator active. A polar curve is defined by the equation r equals theta plus sine of 2 theta for 0 to pi, okay? Notice, by the way, pi is not being included. There's no or equal to sign there. So just something to keep in mind. All right. Part A, find the area bounded by the curve and the x-axis. So this is from 0 to pi. They already gave us the bounds. So the area is going to equal 1/2 integral 0 to pi r squared. R is theta plus sine of 2 theta. D theta. Okay, it's calculator active, so go ahead and plug that into the calculator and make sure you get the number that I get. So pause, plug it in the calculator, make sure you get what I get. Okay, part B. This part can be a little bit confusing, so pay attention to how I do this one. Rewind the video, replay the video if you need to for this part. So it says, find the angle theta that corresponds to the point on the curve where x equals -2. All right, well, x equals -2 is right here. The point on the curve is right here. The angle theta would be from here to here. We want to find the angle theta such that we hit this point on the curve, which corresponds to an x value of -2, okay? So we have to set x equal to -2, but we need to define x in terms of theta. So we know x equals r times cosine theta. We know r has been defined as theta plus sine of 2 theta. Times cosine theta. Go ahead and distribute your cosine theta. This would give you theta cosine theta plus cosine theta plus times sine of 2 theta. Okay, so there's x in terms of theta. And what we want to do is we want to take that and set it equal to -2. So x equals -2 means theta times cosine theta plus cosine theta times sine of 2 theta equals -2. Okay. Now, what I personally prefer to do is take that -2 and add it over. So theta cosine theta plus cosine of theta times sine of 2 theta plus 2. I prefer to set it equal to 0. so that you can plug this into your calculator and just find out where it crosses the x-axis, okay? Now, what you need to do, though, this step's important, and this is probably the step that confuses my students from the past the most, is you need to plug this, you need to reset your calculator, take it out of polar, put it in function mode. Put this into y1 in your calculator, okay? We're just trying to find the value here. These are just representing variables now. We're just trying to find the value that makes this whole thing equal to 0, okay? So plug that into the calculator, find out where it crosses the x-axis. You should get that theta equals 2.786. Okay, so what that means for us is that if this angle was 2.786 radians, an angle of 2.786 radians would land us right here. All right, part C. For theta between pi over 3 and 2 pi over 3, dr d theta is negative. What does this say about the graph on that interval? Okay, so remember that r represents the distance from the pole, okay? R represents the distance from the pole. So if dr d theta is negative, okay, if the derivative of r, which represents the distance from the pole, with respect to theta is negative, that actually means the graph is getting closer to the pole, okay? If dr d theta is negative, that means the graph is getting closer to the pole. Okay, and this should actually make a lot of sense. Think about where pi over 3 and 2 pi over 3 would be. Pi over 3 would be roughly about right here. 2 pi over 3 would be roughly over here. Notice that between about right here and right here, we're getting closer to the pole as you continue along. See, that distance to the pole is getting shorter. Then we get about right here, and then that distance to the pole starts getting longer again. All right, so hopefully that makes sense. All right, part D. At what angle in the interval 0 to pi over 2, so specifically 0 to pi over 2, is the curve farthest away from the origin? Justify our answer. So farthest away, remember that distance away from the origin is r. So we want the farthest distance from the origin. That means we want to know, when is r a max? Okay, well, how do we find out if something is a maximum? Well, you take its derivative, find the critical points by setting the derivative equal to 0, and testing on a sine line. We did that. That's part of like unit 4 and 5. That's with derivatives. So we need to find dr d theta, set it equal to 0 to get our critical points, and then test to see if it's a maximum or not. Okay, so r itself was defined to be theta plus sine of 2 theta. Dr d theta, or r prime, well, the derivative of theta is 1. Derivative of sine of 2 theta is going to be cosine of 2 theta times 2, so 2 cosine 2 theta. If you set that equal to 0, subtract the 1, divide the 2. Okay, this tells us that 2 theta, let's see, cosine is going to be negative a half. Remember, we're only going from 0 to pi over 2. Cosine is going to equal negative 1/2 at 2 pi over 3 and 4 pi over 3, which I know is past pi over 2. But remember, we're going to have to divide these by 2 to get theta. So that'd be 2 pi over 6, which is pi over 3, and 4 pi over 6, which is 2 pi over 3. 2 pi over 3 is not between 0 and pi over 2, but pi over 3 is. So pi over 3 is our candidate for being a max. So we would test on a sine line. Remember, we are restricted from 0 to pi over 2. Pi over 3 is somewhere in between. And we are testing on dr d theta. Okay, so if you plug in pi over 3 into dr d theta, you would find out, well, not pi over 3, but plug in something between 0 and pi over 3. That could be like pi over 4. Remember, this calculator active, so you can just use your calculator to test values. If you test something between 0 and pi over 3, you would see that your derivative would be positive. If you test something between pi over 3 and pi over 2, you would see that your derivative would be negative, which makes pi over 3 the angle where r is a max. All right, so the curve is farthest from the origin. Or from the pole, origin, pole, doesn't matter. When theta equals pi over 3. All right. One more example, then we'll be done with this set of notes. All right. The graph of the polar curve 1 minus 2 cosine of theta for theta between 0 and pi is shown. Let S be the shaded region of the third quadrant bounded by the curve in the x-axis. First, write an integral expression for the area of S. Now, this one, a little bit deceptive. We have to be careful with the angles here. This is actually theta equals 0. This point is theta equals pi over 3. This is when theta equals pi. Okay? You can see that if you go and graph it in your calculator. If you graph it in your calculator and you trace it, you'll see that this is the point that corresponds with theta equals 0. Another way you can actually see it is test it. If you plug in 0 for theta, cosine of 0 is 1. 1 minus 2 times 1 is negative 1. You see how that points at negative 1? So you can actually see it that way as well. Okay? So if I want to write an expression for the area of S, well, S is running from 0 to pi over 3. So we have the integral 0 to pi over 3. Again, you can pull the 1/2 out if you want to, or you can leave it on the inside. 1/2, and then it's going to be r squared. 1 minus 2 cosine of theta squared d theta. All we had to do was write the integral expression. So yeah. And by the way, another way, especially if this was no calculator, so that it's easy to see that this one is 0. You just plug 0 in, you get negative 1. You can tell what this is by setting this equal to 0, because that's at the pole. So let's show that real quick. If you did 1 minus 2 cosine of theta equals 0, negative 2 cosine of theta equals negative 1, cosine of theta equals positive 1/2. We know that cosine is equal to 1/2 when theta is pi over 3. So that's another way you could tell that that was pi over 3 right there. Okay. All right, let's write expressions for dx d theta and dy d theta. We know x equals r cosine theta. We know y equals r sine theta. So r is 1 minus 2 cosine theta. times theta, or sorry, times cosine theta. Actually gets a little bit more space here. All right, distribute that. We get cosine theta minus 2 cosine theta squared. Over here for r sine theta, so again, r was 1 minus 2 cosine theta. This time we're distributing sine theta. And let's go ahead and write our expressions for dx d theta and dy d theta. So the derivative of x with respect to theta, that's going to be negative sine theta. Here we're going to do power rule with chain rule, so it's going to be negative 4 cosine theta times negative sine theta. If we simplify this, we get negative sine theta plus 4 cosine theta sine theta. All right, dy d theta. Derivatives, so take the derivative of this right here with respect to theta. We're going to get cosine theta minus, and we got to do product rule, 2 cosine theta times cosine theta, plus, by the way, tricky little part right here. This negative right here is applying to the whole product rule. Be a little careful with that part. Let's see, continuing the product rule, then times sine theta times negative 2 sine theta. So we have cosine theta minus 2 cosine squared theta minus, or this one will be plus, you distribute the negative to something that's already negative, you're going to get positive, plus 2 sine squared theta. All right. Just double check that that's correct. Let me double check with my key. That looks good for dx d theta. That part looks good for dy d theta. All right. And then finally, write an equation in terms of x and y for the line tangent. All right, so we've done this in previous sets of notes. Yeah, we need to do y minus y1 equals m times x minus x1. Our slope is dy dx such that theta equals, where they want it at, theta is pi over 2. So that's going to be dy d theta over dx d theta such that theta equals pi over 2. All right, go ahead and calculate. We have our dx d theta and dy d theta. For the dy d theta, we plug in pi over 2. Let's see, cosine of pi over 2, that's 0 times 0. So it's looking like we're just going to get a 2 on top for dx d theta at pi over 2. Negative sine of pi over 2, that's going to be negative 1 plus 4. And then that's going to zero out because cosine of pi over 2 is 0. So we get 2 over negative 1. So our slope is negative 2. All right. Then we just need to calculate x and y when theta is pi over 2. Then we'll be good. All right, x when theta is equal to pi over 2. We're just going to get cosine of pi over 0. Yeah, we're going to get a bunch of zeros there. Y when theta is equal to pi over 2, we're going to get 1 minus 0, which is 1. All right, then we write our equation. Y minus 1 equals negative 2 x minus 0. And we're done. All right, y'all. Hopefully these notes made sense.